Hey folks, so this video is going to feature a couple things. The first one is I'm going to talk about moment of inertia for a couple minutes, and then the second thing is we're going to do one problem that relates to Newton's second law for rotation. So in your textbook, this is on page 242, and this is the way that moment of inertia pops up for particles. So question 10 is like a focus on concepts. So the drawing shows three objects rotating about a vertical axis. The mass of each object is given in terms of m naught, and its perpendicular distance from the axis is specified in terms of r naught. Rank the three objects according to their moments of inertia. And so as far as moment of inertia goes, we had this equation from last time, but because we're talking about individual particles, which like a massive sphere is a particle, the moment of inertia is really just m times r squared. And so, your job here is to rank them, and this is like one of the only situations where you would actually use this equation. And so let me just do that and you can see the results. So for object A, it has a radius of r naught and a mass of 10. And so the moment of inertia for that one, and you'll see this in a minute, is going to be 10 m naught times r naught squared. So really, when I simplify that, it's just 10 m naught r naught squared. So that's the work that I would show for that one. Pretty simple. And so everything else is still in terms of m naught and r naught, so I can make this comparison. So for object B, or for mass B, it's a distance 2 r naught away, and the mass is 2 m naught. And so for object B, the moment of inertia would be 2 m naught times 2 r naught squared. And so before I do the actual math, I just want to show you what that looks like. It's twice the radius, but because of the way the moment of inertia equation works and depends on r squared, it's really 2 squared is the change in moment of inertia. So when I simplify this, I have 2 times 2 squared, so 2 times 4, it's really 8 m naught r naught squared. So let me just show you what's significant there. This one has 1/5 the mass of the other one, but because it's twice as far away, it's 80% or 8/10 or 4/5 the moment of inertia. So significantly lighter, but because it's further away, the moment of inertia is almost as large. And so to take care of object C is, the mass is just m naught, so it's the lightest one of all, but the distance away is 3 r naught. So for C, I would have m naught as the mass, and I would have 3 r naught as the radius. And so this is 3 squared, or 9, and so the moment of inertia is 9 m naught r naught squared. And so these are the three moments of inertia as they relate to one another. So this is largest to smallest, and so the answer would be A, C, B. So this really just is there to hammer home the idea that the distance that an object is away from the axis of rotation has an overall greater effect on moment of inertia than the actual mass of it. So that's the first thing I wanted to talk about. The second thing I wanted to talk about was why you don't really need to worry about moment of inertia as something that you calculate based on mr squared. And so I just wanted to show you this screenshot from your textbook, or not from your textbook, but from a website. These are equations for moment of inertia for specific, frequently encountered shapes of objects. So something that you would do in like a college physics class is you would use integral calculus to come up with a general expression for the moment of inertia of an object of a particular shape rotating around a particular axis. And in AP Physics 1, in general, we just kind of shy away from it, at least the test does. But for me, in this class, you would have access to this information. And so you'd just be you would be told what type of object it was, and you would also potentially be told what its general equation for moment of inertia is. The concept, however, is very important, and so I want to start with this hoop about symmetry axis. So a hoop is quite literally hollow in the middle. So imagine even this with just nothing in the middle. These equations for moment of inertia show you how the concept of moment of inertia appears in equations. Basically, when this thing rolls or rotates, it rotates around the very center of this bar. And what you want to notice is there's a whole lot of nothing in the middle of this shape. What you actually have is almost all the mass is focused around this hoop and then these two masses, and very little of the mass is with this bar right here. So this object has almost all of its mass shifted all the way out to the edges. And so its equation for moment of inertia is mr squared, meaning the total mass of this object times its radius squared. And that goes for every particle. That's the biggest equation on this sheet. Everything else is actually smaller than that. And so to give you like a contrast, that's like rotating around its center. To contrast that, one to the left is the solid cylinder or disk around the symmetry axis. So it's the same thing, but it's as if you filled in everything in the middle. If there is nothing but solid in the middle here, the moment of inertia actually goes down to 1/2 mr squared. So for that first object, the solid cylinder, the mass is evenly distributed everywhere, and so its moment of inertia is actually smaller than that of the hoop. So it's again like a shift in your thinking, but what you want to see is like there are some objects where the mass is uniformly distributed, and then there are some where it's distributed outward as much as possible, and then everything in between. So to go through kind of all these shapes, there's two more things to talk about. There's the hoop about the symmetry axis and the hoop about the diameter. When you change the axis of rotation, you actually change the moment of inertia. And those of you who play tennis might be familiar with this, that if you take a tennis racket and hold it by the handle and spin the handle, the face of the racket just kind of like flips over and over again. And it's pretty easy to flip it that way. You can just like kind of flick your wrist and the tennis racket rotates. But if you actually take the tennis racket and like throw it up in the air, like hold it by the handle and throw it up in the air, almost like you're flipping a fried egg over. If you flip it like that, you have to put more force into getting that rotation because you're rotating it around an axis where more of the mass is further apart. I will try and demonstrate this in class. I'll try and bring a tennis racket in. And so just by changing the axis of rotation, you're changing the moment of inertia. And then the other thing is just to kind of review that, the first idea. We have a solid sphere and a thin spherical shell. So obviously you're limited by the fact that this is like a textbook, a two-dimensional textbook. This solid sphere, imagine like a bowling ball or a softball or a baseball, where there's mass all throughout the sphere. And then the thin spherical shell will be like a basketball or a tennis ball, where there's air in the middle, and those rotate with different inertias. The moment of inertia equations are very similar, but 2/3 is greater than 2/5. So if you hollow out a spherical shell, the moment of inertia equation gets bigger. Now, if you actually like take the mass out of a sphere, then the moment of inertia is going to get smaller because you're actually removing mass. But if you had like a solid sphere and you just managed to like get in there and push all the mass out to the edge, then you would increase the moment of inertia because you're moving more of the mass away from the center. So we'll talk about that in class, but that's just something that I want you to think about today. Okay, the last thing I wanted to do is do this problem. And so this is a Newton's second law for rotation problem. I've not done this before, so it's going to be like kind of slow. You might want to speed up the video or pause and try this on your own if you're feeling pretty gung-ho, because I'm going to be going through it the first time right now. So we have a ladder that is almost 10 meters long. It's pretty heavy. It's lying flat on the ground. The painter grabs the top end of the ladder and pulls straight upward with a certain force. at that instant, the ladder experiences an angular acceleration about the bottom of the ladder. So basically, like, if you lift one end of the ladder, the other end is going to stay on the ground, and so you will cause the ladder to rotate. And then based on this, what is the ladder's moment of inertia? So we're going to start with a free body diagram and just go over one of the kind of major rules here. So the ground and the ladder are going to be in the same location. So I'm going to draw the ladder like this. And the axis, oh, you can't see that. And the axis of rotation is going to be here. So this is the bottom of the ladder. And, you know, there is ground here. And we're going to be careful about what we do with the ground. So the painter comes along and grabs the other end of the ladder and lifts straight up with a force of 245 newtons. So we'll just call that F. And the important thing to note is that that cannot be the only force acting on the ladder. There is the ground exerts a force, and the ladder itself has a weight. So let's do the weight of the ladder first. The weight of an object, of an extended object, happens at its center of gravity or its center of mass. And for extended objects in this class, that's going to be right at the middle. And so that is going to be the force of gravity for the weight of the ladder. Now, just so we're clear that that's the middle, the ladder has a certain length, and so when you put the gravity vector in, you essentially divide the ladder in half. And so the weight of the ladder happens at a distance of r over 2, and then that 245 Newton force happens at a distance r. Now, when you start to lift the ladder, it's still touching the ground. The only part of the ladder that's touching the ground is here, and so there's going to be a normal force there. So we start with the free body diagram, and that's going to guide all of our work when we do this. Cool. So we're trying to find moment of inertia, so we're going to try and find net torque, and we have angular acceleration. And so that's, like, oddly enough, that's it. So at this point, we can go straight to saying the net torque is equal to I alpha. Now, we have alpha, it's 1.80 radians per second squared, and so it's going to be the net torque that is tricky. So I'm going to slowly expand this equation, and so now I identify the axis of rotation is going to be the bottom of the ladder, because when you lift one end of the ladder, the other end is going to stay put on the ground. There's even going to be a friction force, but what's nice is that it doesn't matter what forces there are, because any force at the axis produces a torque of 0. Okay, so as far as net torque is concerned, we need to add the torque due to force F and the torque due to mg, and that's going to be equal to I alpha. Again, I don't need to include the normal force because it's right at the axis of rotation. It produces no torque. The torque due to force F is going to be R times force F, and it's going to be positive. Now, the convention is that counterclockwise is positive, but it doesn't matter. As long as you're consistent with all of your directions, then you'll be fine. So counterclockwise is positive, so R times F is the torque there. Now, the weight of the ladder, that's going to be a negative torque, so minus, and then the R for the weight is R over 2, and then mg is the magnitude of the force. And then that's equal to I alpha. And if you want to be really fancy, you can simplify this, and you can say that the value of I is going to be Rf minus Rmg over 2 all over alpha. So if you wanted to plug everything in all at once, you could. If you look at this question in the book, it's in the back of the chapter on torque. It does ask for the net torque, and so you could just calculate Rf minus R over 2 mg. before you calculated I. But since we're just finding I, that's it. So free body diagram, go to the second law equation. There wasn't anything like extra funky going on here, just two torques that produce a net torque. Okay, so the value of I is going to be the radius of, or so basically the length of the entire ladder, 9.75 meters, times that force, 245 newtons, minus RMG over 2. So I'm just going to turn that into 1/2 RMG. 1/2 9.75 meters times 23.2 kilograms times 9.81 newtons per kilogram, all divided by alpha, and so 1.80 radians per second squared. So whatever that's equal to, that's going to be my moment of inertia. Okay, so 9.75 times 245 minus 1/2 times 9.75 times 23.2 times 9.81. So net force is net torque is 1,279 newton meters divided by 1.80. The moment of inertia 710.7. So really we'll just go with 711 kilogram meters squared. And there you have it. So this ends up being kind of like a beginner Newton's second law question, and so in class we'll be tackling some more challenging ones. There we go.